All right, so after presenting how Bohr did all his calculations in algebra, awesome. On paper, he's able to calculate the wavelengths of light that are emitted in emission spectra. And he's able to solve some problems that Rutherford had in his satellite model. So over here we have Rutherford's model where he proved through the Geiger-Marsden experiment that the nucleus is a positive charged core. Electrons are kind of these satellites that are orbiting around that nucleus, and everything's fine. Now in Rutherford's model, these electrons are randomly orbiting satellites. They don't have energy levels. And a big problem here is that when any electron is undergoing circular motion, it's experiencing centripetal acceleration. If you accelerate a charge, okay, it's going to generate an oscillating magnetic field, which it means that it's generating electromagnetic field, which means it's going to be generating light, and light is energy. So these electrons should be losing energy as they're undergoing circular motion, and that's what this diagram is showing. There's a catastrophe. As these electrons are orbiting, if they behave like particles orbiting, they should be losing energy, and eventually they would spiral into the nucleus. And if a negative charge meets a positive charge, it would annihilate. Okay, so you'd read about that in this chapter about the pair annihilations. But if an electron meets a proton, they would annihilate into a ball of light. And so basically all matter should disappear instantly if Rutherford's model was correct. Okay, now Bohr's model said that those electrons exist in shells, in orbits, in stable orbits, and aren't randomly orbiting in that way. Still, they're undergoing circular motion because Bohr considered the electrons as particles, as satellites as well. So they would also be undergoing circular motion. So they should technically, even though they're in stable orbits, they should still be losing energy and spiraling out because they should be radiating. So Bohr's model, although it was able to calculate the wavelengths of the emission spectra, Bohr's model also has problems, but we'll talk about that later. So Bohr's model at least explained the absorption and emission spectra very well. Okay, and it suggests why electrons do not spiral in the nucleus, because for some reason they form these shells where the shells have conserved angular momentum. So these electrons are orbiting, and he was able to make this connection that those orbits relate to some type of wavelength or like standing wave, but he didn't fully explain that until other people came in and kind of adapted his model. Okay, but his model said that they have these stable shells, and those stable shells should fit a fixed amount of wavelengths of the electron waves. However, the weaknesses of his model, and this is important because on the IB exam, you will have to explain weaknesses of each individual model. It still assumes that the electrons orbit, okay, which are particle orbits, and they would technically crash, as I described above. And it can't explain why some lines are brighter than others in the spectra. Okay, so if you look at an emission spectra, some lines are brighter than others. Why would that occur? And it can't explain some fine structure. Some of those lines have little lines beside it, so it can't explain any of that. So with every model, there are some pieces of evidence to say that the model is incomplete, and that's important for you to know. Rutherford's model had aspects that were incomplete. Bohr's model has aspects that are incomplete. So it allows other scientists to build, to design new experiments and build on top. And that's what we're going to talk right now. So after Bohr's original model, the first amendment was to think about it. Let's get rid of the idea that the electron is a particle. Everyone likes the idea that these electrons are form shells because they form these kind of standing wave structure. So we're going to think about the particle of an electron in terms of an actual standing wave trapped in the boundaries of a box. And this is called the particle in a box model. So if I think about this electron that's moving back and forth bound between a boundary, okay, remember waves reflect off boundaries. This electron is moving back and forth in the boundary of the radius of an individual shell. Imagine that shell has these boundary walls. Well, if that electron is bouncing back and forth, that electron, let's forget about the idea that it's moving as a particle. Let's just think about it as a wave. When a wave moves and reflects off of a boundary, it changes its phase and it undergoes interference, and it makes these standing wave patterns. This would be my fundamental wave, standing wave. This is my first harmonic with a node. These are nodes would always form at the boundaries. Okay, so this is the first harmonic, this is the second harmonic, third, and so on. And if my wavelength isn't perfect and in those boundaries, I'm going to get interference. Okay, that's what this is showing. So this would be a wavelength that doesn't fit in those boundaries. It's forming interference, so it would cancel out. Now, if I think about an electron as a standing wave, that's really the only way I can think about how certain wavelengths are selected for certain radii. Okay, so that's just kind of the idea. Let's find a way to explain Bohr's model without using particles, without using matter, and let's think about it in terms of a wave. That's what it says over here. So can we derive the same equation? Can I get this equation, E is equal to negative 13.6 electron volts over n squared? Can we get that by redesigning Bohr's derivation just in terms of standing waves, and that's what we're about to try to do. Okay, so the energy of each orbital is calculated purely from a wave model. So in that case, how are we going to be able to do that? How would I describe a standing wave in this form? So for the rest of this, you're going to watch and pause along the way to kind of understand what's happening as I'm deriving this. Okay, so here's a diagram that shows the finished product. If I try to build a model where I'm just looking at waves in that radius and forming a standing wave, we're going to get this. The energy of that standing wave is going to be equal to n squared times Planck's constant squared divided by 8 times the mass of an electron times the radius of whatever orbit I'm looking at squared. Okay, so we're going to be able to derive that by the end of this. And if I know the different energy levels, n and 1, 2, 3, 4, those energy levels correspond to different radii, I'd be able to calculate the energy at each of those orbits. If I know the energy, I'll be able to calculate the wavelength of light that is emitted per transition. So let's start to go through this process. So if you remember, here's a standing wave, and if that's the length of the standing wave, the wavelength of that standing wave, so remember back to musical instruments and standing waves, the wavelength is equal to 2L. Okay, so in our standing waves unit, n lambda, this is the harmonic, is equal to 2L. Okay, so if this is the second harmonic, lambda is equal to L, and so on and so on and so on. So if you forgot about that, this is a good chance to review standing waves, which is nice, right? So you're going to do that for your mock exam. Now, a cool thing that we can do is we know that according to de Broglie wavelength, lambda is equal to h over the momentum. So I substituted that in over here. Okay, now I have an expression over here where I can then rearrange this expression to solve for the velocity of electron. Remember, in Bohr's model, he needed an expression to be able to solve for the velocity of an electron. So if I think about it just in terms of a wave, here's another expression that would allow me to calculate the velocity of an electron without actually measuring it. So that's kind of cool. So nh over m2l would be the velocity, okay? And so now, if I know the velocity, I can actually plug it into here and solve for the kinetic energy of the electron in an orbit, okay? So 1/2 m, plug that in, squared. If I apply the algebra through, it would give me that, okay? That was quick and easy. So we were able to get that expression that we saw over here in just 2 steps. So the particle in a box model is quite simpler than Bohr's original model. And that goes along with what Einstein said about Occam's razor. So Einstein proposed this idea that, the simplest answer is going to be the truth, using something called Occam's razor. So there's many ways that we can derive an expression or a value in physics, okay? But Einstein would say that the most simplest and elegant way to do it would probably be the most correct way to describe the phenomenon. So here we have a simpler method. So maybe the wave model is a simpler and more correct way to think about it. Okay, but what does L represent? So L in this case represents the boundaries that are binding this. Now the radius is changing for every orbit. Okay, so the boundaries is actually the radius that we're looking at. So for every shell, the shell is going to have a different radius, and it depends on how many wavelengths can fit in that circumference. So the smallest would have only 1 wavelength. The next one would have 2 wavelengths, okay? And so I can plug that in, and I could be able to solve for the radius of every standing wave. So L, in this case, must fit a whole number of wavelengths, okay? So if I plug that in, okay, 2 pi r for the length, all right? And I put this through in the algebra, okay? Now my kinetic energy in terms of the radius, the actual radius, is going to be this expression, which is what I showed up top over there. And that's the full thing. So if I'm able to calculate the radius of each orbit, I can know what orbit that is. I'll be able to calculate the total kinetic energy of that electron in that orbit without considering that electron as being a particle. Now that's super important. So what's really cool is if I went in and I know the radius of a shell and I plug all these constants in, I get the exact amount of energy that I would have got in Bohr's original calculation. So this is really neat. We looked at it in a different way and came up with the same solution. And in this method, we don't have to think of the electron being a particle that is orbiting and losing energy and to crash in. So this is a more truthful way of looking at it. Okay, so another way to solve the kinetic energy, which is a little bit simpler and easier than what I did above, is to think about it in terms of momentum like this. Okay, so lambda is equal to 2L over n. That's the standing wave. And this is the de Broglie equation. So here I've just equated those two things, right? And if you follow my logic where I'm thinking about kinetic energy in terms of momentum instead of 1/2 mv squared, it leads me to the answer a lot quicker. Okay, so on an IB exam, it would be very rare that they're going to ask you to derive this from scratch, but they might take you from here and say, okay, how does this take you to this? All right, so it could be, I could see a 3 or 4 mark question on paper too. I've seen it a few times. Okay, so they'll give you some part along the way and they'll ask you to prove how one of these equations is created. Now, if I plug all this in through, all right, check this out. If I know the radius at a certain point, I will be able to get that same expression that we got in Bohr's original model. So that brings us to a close about this idea of a particle in a box. And the big idea here is that all these models change based on our concept. We always look back at a model and we say, okay, well, that can't be true. So how can I recreate the model conceptually to be true with what we know? And the particle in a box model allows us to model the same stuff that Bohr did, but without considering it having anything to do with an orbiting particle. In this case, we're considering it to be a standing wave, and we applied the logic of a standing wave to get the exact same expression, which really resonates to be a truth.